Hello students, welcome to EPG Pathshala. I am Dr. Rajkishore Sharma from Chemistry Department of Delhi University. Today we are going to talk about introduction and instrumentation of reflectance absorption infrared spectroscopy under the paper on surface analytical techniques 2. First, let us see what we are going to learn in this presentation. We will be dealing with introduction of RAIRS. This includes the following topics that will be discussed subsequently. These are classification of vibrational spectroscopy and defining them, principle behind RAIR technique and describing the selection rule, and what are the specifically metal surface selection rules. Moving on to the instrumentation of RAIRS, following features will be elaborated throughout the presentation. These are the optical arrangement, purpose of using alkali halide lens or arrangement of mirrors, use of beam splitters, role of sensor card, advantages of RAIR, and working of the instrument. Vibrational spectroscopy is bifurcated into IR spectroscopy and electron energy loss spectroscopy. Further, IR spectroscopy divides into transmission IR spectroscopy, diffuse reflectance IR spectroscopy, multiple internal reflection IR spectroscopy, and reflection absorption IR spectroscopy, that is RAIRS. We will be briefly discussing about the types of spectroscopy in the next slide and will develop a thorough understanding of reflection absorption infrared spectroscopy. The historical development. Much of the information concerning the bonding and symmetry of molecule in the gaseous, liquid and solid state has come from the study of molecular vibrations using infrared spectroscopy. It seemed, therefore, only natural that infrared spectroscopy should be extended to provide a vibrational spectroscopic technique for the study of the adsorbed phase. The first step in this direction appears to have been taken by Boswell et al. In 1938, extending the traditional transmission IR technique to study the adsorbed water on Montmorillonite clay surfaces. It was not until 1950 that the IR transmission method was again taken up by the several research groups to study adsorbed species on high surface area materials. Perhaps the most remarkable of these experiments was the work of Ishens and co-workers in 1956, who studied the adsorption of carbon monoxide on supported nickel, palladium and platinum catalysts. A comparison of the spectra obtained on the catalysis with those of various metal carbonyl complexes enabled then to assign bands to various adsorption configurations, that is, linear and bridging, and to recognize the influence of vibrational coupling of CO stretch vibrations of adsorbed carbon monoxide. Since the number of molecules with which radiation can interact in the two-dimensional adsorbed phase is orders of magnitude lower than typical bulk samples, it was important that high surface area systems were used in the early IR studies of adsorbates to ensure a considerable contribution from the surface as distinct from the bulk of the sample. This was indeed the rationale behind the use of thin, that is 100 to 400 angstrom, porous evaporate metal film for the study of adsorbed molecules on metals by IR transmission. These samples transmitted a reasonable proportion of the incident radiation, that is absorption due to the bulk metal, and exhibited a large effective surface area so as to increase the proportion of surface absorbers. The high area porous films and supported metal catalyst, however, exhibit a rather heterogeneous and difficult to define surface, and a growing awareness of the structural influence of the surface on chemisorption and catalysis led to the study of adsorption on clean, annealed, polycrystalline and ultimately well-defined single crystal metal surfaces prepared under ultra-high vacuum conditions. Two main experimental considerations arising from such a proposal were the following. Since the metal is non-transparent or non-transparent to IR radiation, experiment would have to be carried out in reflection. The absorption experiment would have to be capable of detecting very low absorption intensities. The transmission experiment on high surface area supported catalysts and porous metal films, although having fewer surface absorbers in a typical sample, that is approximately 10 to the power 16, then the bulk phase, which is approximately 10 to the power 18, has considerably more than in a few monolayer on a well annealed polycrystalline surface or the surface of the 10 into 10 millimeter single crystal, which is approximately 10 to the power 14. Initially, it was believed that the only way to overcome the sensitivity problem was to reflect the radiation several times from the surface, increasing the number of adsorbate molecules with which the radiation could interact. Thus, the first use of multiple reflection from the study of adsorbed monolayers on annealed metal films, and therefore, strictly speaking, the first use of reflection at absorption infrared spectroscopy or RAIRS was by Pickering and Ecostrom and Francis and Ellison.
We would talk about various other kinds of such spectroscopies. The first of this kind is electron energy loss spectroscopy. It is in short called EELS. This technique is also known as the electron analog of Raman spectroscopy. The vibrational spectroscopy of the surface species is measured by utilizing the inelastic scattering of low energy electrons. It is also sometimes referred to as HREELS, high resolution electron energy loss spectroscopy, or as we call it, high resolution EELS or VELS, vibrational ELS, as the other name goes for this. The second is transmission IR spectroscopy, abbreviated as TIR. This study is often used for supported metal catalysts having high surface area and permits a high concentration of adsorbed species as a sample. The basic experimental geometry used in this technique is very much similar as that of liquid samples. However, the sample should be IR transparent over a considerable range of wavelength. The third in this series is called diffuse reflectance IR spectroscopy. In short, it is called DRIFTS. This technique also implies a high surface area catalytic samples, but it is applicable to those samples that are not sufficiently transparent to be identified in transmission, etc. In this diffuse scattering of the IR radiation, for the sample taken or the sample that we take, this takes place, which is further collected, refocused and analyzed. However, for analysis of low surface area samples, for example, single crystal, these techniques are employed very efficiently. Deals with the other two kinds, multiple internal reflectance spectroscopy, also called multiple internal reflection spectroscopy. In short, it is written as MIR. This technique involves the phenomenon of total internal reflection, in which IR radiation beam is passed through a thin sample, causing reflection from the front and the rear faces. IR radiations on each reflection are absorbed sometimes by the species on solid surface, therefore also known as attenuated total reflectance, ATR also. Reflection absorption IR spectroscopy, also known as RAIRS. This technique requires a highly reflective sample, for example, a metal single crystal surface. The front face of the sample reflects the IR beam, specularly giving rise to the signal. Explains reflection absorbance IR spectroscopy. This technique involves the identification of absorbent present on metallic substrates. Here, a substrate has been shown on which IR source is sending light or rays, and they are reflected going to a detector where IR detects the required kind of analysis. This explains what is RAIRS or RAIRS. This acronym RAIRS means Reflection Absorbance Infrared Spectroscopy. Provides the most definitive means of identifying the surface species generated upon molecular adsorption and the species generated by the surface reaction. This is used to obtain vibrational data from solid state or gas phase samples. Excellent energy resolution, that is less than 2 centimeter inverse, are useful for separating multiple peaks of phase transitions or lateral interactions and dynamics of coupling. The last is straightforward instrumentation, which one has to learn in order to understand this particular spectroscopy. Talks about selection rules, which one uses for IR active mode or IR inactive mode. This has been shown in this slide as a surface where IR active mode and IR inactive mode would be reflecting when we carry out these studies.
The vibrational modes of the adsorbate on the metal substrates rely on the surface dipole selection rule. The selection rule states that only those vibrational modes will be IR active and give rise to observational bands that have oscillating dipole perpendicular to the surface. The interaction of electric field of infrared incident light with dipole moment of the molecule excite the vibrations of the molecule in gas phase. If the selection rule of the electric dipole transitions are satisfied, the vibrations are said to be infrared active. We can say that del mu upon del q k is not equal to 0. Here mu is the dipole moment, q subscript k is the normal vibrational coordinate. The derivative is called dynamic dipole moment of the molecule along the normal coordinate qk. The dielectric behavior of the metal also influences the absorption of light by a molecule on a metal surface. The dipole moment of the adsorbed molecule and the electric field of the incident light interact with the metal electrons on the metallic surface and thus imposing metal surface selection rule, that is dipole selection rule.
Explains metal surface selection rules, or in bracket as we have written MSSR, which obviously stands for metal surface selection rules. The first in the series here is dynamic dipole moment component that is perpendicular to the surface and will only excite the vibration if this condition, which has been indicated on slide, is shown. That is, the change in the dipole moment
Is not equal to 0.
The metal electron screens the parallel component of the dipole, generating an image dipole that is opposite to the molecule. The second is, which talks about the rule, the second rule states that the incident light should have a component that is polarized. The component having electrical surface perpendicular to the surface is P-polarized. Due to destructive interference, the electric field parallel to the surface disappears.
Reflection adsorption infrared spectroscopy offers a means of probing vibrations at surface with high resolution and with its ease of implementation and strict selection rule is a convenient technique for verifying molecular integrity and orientation of metal surfaces. The ability of RAIRS to identify surface species when combined with the quantitative attributes of low energy electron diffraction, that is LEED, L-E-E-D, results in a powerful tool for surface structural determination. Its insensitivity to ambient gas pressure also makes RAIRS ideal for studying catalytic reactions under a wide range of pressure conditions. The maturity of RAIRS as a standard surface analytical technique is exemplified by the results that have emerged from laboratories over the past decade. Our focus of attention from the early use of RAIRS as a simple structural characterization tool to characterize simple diatomic molecules such as carbon monoxide and NO, nitrous oxide, on low Miller index crystal planes, to its present application in the journal exploration of several important themes in the surface vibrational spectroscopy of the identification of novel surface intermediates, the determination of adsorbate bonding geometries, the elucidation of surface reaction pathways in catalytic reactions, and studies on metal supported thin oxide films. Going back to what is P-polarized light. Light in a well-defined polarization state either parallel, that is P-polarized, or perpendicular, that is S-polarized to the plane of incidence, impinges on the surface at a well-defined and controlled angle of incidence. The reflected light is detected at an angle equal to the angle of incidence. The polarization state of the beam and surface pressure sample are computer controlled and adjusted as desired. S-polarized light almost cancelled by reflection at grazing incidence. P-polarized light almost doubled by reflection at grazing incidence. Only P-polarized component light can be reflected from surface at a high incidence angles.
If you look at it, explains best sensitivity parameters for observing and absorption in RAIRS. The parameters are P-polarized light, grazing technique, or grazing incidence as we call it. Molecule with transition dipole arranged along surface normal. This emerges out of selection rule. Molecule with large transition moment. Now this explains the kind of transitions which one gets, and under different modifications the kind of various IR spectroscopies or vibrational spectroscopies that would arise. Now what is the instrumentation of this particular kind of spectroscopy? So let's talk about the instrumentation. The instrumentation involved in this kind of vibrational spectroscopy in general. So optical arrangement for performing RAIRS has been shown, and you can imagine how simple it is, that some kind of a light is indicated on this and the reflected portion is analyzed.
Two ultra-high vacuum chambers are currently being used for RAIRS studies of molecular adsorption and catalysis on metal single crystal surfaces. Both systems have standard facilities for sample cleaning and characterization using LEAD, OJ electron spectroscopy, AES, and temperature programmed desorption spectroscopy, we call it TDS. One of UHV systems has a novel transfer mechanism that allows efficient sample transport between the UHV system and a coupled infrared cell that can be isolated and pressurized to 1 atmosphere. The second RAIRS system is dedicated to UHV experiments and is currently being equipped with a simple thermal molecular beam that will allow measurements of sticking probabilities and hence the coverage, and the characterization of the reaction products from the surface alone. This experiment is mostly carried out with the sample placed in a UHV chamber, which is relatively large and is used for a range of other surface analytical techniques. The infrared beam is extracted from the spectrometer, focused into the UHV chamber, reflected from the surface under consideration, and further refocused onto the detector using the optical arrangement. Figure 1a displays the most typical configuration of that shows the deflection of the beam after passing through the interferometer and then out of the external port with which most commercial FTIR spectrometers are fitted. Now about function of a beam splitter. The beam is further refocused onto the external detector after reflection from the surface, which is further fed back into the processing circuitry of the spectrometer. The beam splitters used in the mid-infrared FTIR instrument show relatively poor transmission of visible light, which poses a major disadvantage of the visual alignment of the optical path external to the spectrometer. As far infrared beam splitters are completely opaque in the visible, the best solution is the alignment of the beam visibly using a near infrared beam splitter that transmits properly into the visible and further replacing this with appropriate mid or far infrared beam splitter for the spectroscopic measurement.
Talks about role of sensor card. Instead, a sensor card that emits visible light when struck by IR radiation is used, but the UHV environment in the vicinity of the sample ensures the sensor card that it cannot be used in just that section of the optical path where alignment is most critical. To overcome this problem, the source is placed immediately before the sample, focusing the reflected beam from the sample directly into the interferometer detector And this section of the spectrometer is responsible for the detection of rays, as shown in figure 1b earlier. At the sample portion, the beam appears to be much brighter visually. Let's come to detector, about the detectors. The detector used in RAIRS investigations in the mid-infrared range, another name for this, are liquid nitrogen cooled mercury cadmium telluride detectors. They are known as MCT detectors. These detectors having these saturation levels are the ones which are used for detectors position. These MCT detectors perform good over a wide wave number range, although in recent years their performance at longer wavelength has also improved dramatically. But when these studies are conducted in far infrared regions, copper-doped germanium photoconductive conductors or biometric conductors formed from heavily doped silicon or germanium are also used in general.
Following are the advantages of RAIRS technique. RAIRS can be easily added to the existing UHV apparatus without complicating the vacuum system or spectrometer. Occasionally changes in one or both of these required to utilize a particular advantage of this technique. Considering other surface spectroscopies, one major advantage over the other technique is the interaction of infrared photon with gas phase species is relatively weak. This is especially those involving electrons or ions as a surface probe. Hence, RAIRS can be used to analyze or study the surfaces even in the high ambient pressure of gases and can also serve as in situ probe in the reaction conditions. Therefore, it bridges the pressure between the UHV condition and superatmospheric pressure. Superatmospheric pressure that is used in many commercial processes such as catalysis. Hence, many efforts are being made to exploit this possibility of modifying a UHV with a RAIR high pressure cell so that the sample can be prepared and characterized under UHV conditions.
The disadvantages associated with the design. So disadvantages of the design will be the major disadvantage of this particular design in comparison to that of figure 1a is that the more thermal infrared emission from the room temperature beam splitter from cooled detector receives. The problem of beam splitter emission can be virtually eliminated by the reduction of detector acceptance angle for RAIRS, but this has rarely been attempted. RAIRS involves detection of very minute change in the level of signals, that is the change in reflectance followed by the change in the absorption is generally less than 1% or maybe less than 0.01%. Talks about how it works. Infrared light induces vibrational transitions in molecular bonds, and by measuring the frequency and intensity of the absorbed infrared light, information such as chemical environment, structure, and the functional group identity can be elucidated very properly. Infrared radiation is directed from the source through a series of gold-coated mirrors towards the surface of material under test. The impinging photons interact with the surface molecules and reflect from the crystal substrate. The reflection beam are directed and focused into the detector through series of gold coated mirrors. The raw signal is then Fourier transformed into the familiar frequency domain. The detector which we see, it goes through a series of gold-coated mirrors, and then we find that this raw signal is then Fourier transformed. The mathematical basis of reflection infrared spectroscopy was developed by Greenler in the year 1960s. Gives a flow diagram of this particular kind of spectroscopy, wherein we use the detector and the analyzer are both given here. Brown et al. Described the most radical design of the UHV system and FTIR spectrometer for applications in rare systems. This deals with the setup. The setup was primarily designed for infrared emission and chemiluminescence, but also served the purpose for RAIRS after the addition of potassium bromide windows. This setup was designed to reduce the thermal signals to considerably low values. The entire path between the sample and the detector is masked in a light-tight enclosure in liquid helium cooling. Liquid helium temperature are also required in the optics of FTIR spectrometers. Also, unacceptable heat description in the cryogenic enclosure due to the laser operating here. Therefore, the moving mirror is sensed capacitively. Cadmium doped germanium flow meter is used for the detection of most sensitive experiments at an operating temperature of 0.3 degrees Kelvin that exhibits noise levels that are 2 orders lower than the convention MCD detectors, which have been used earlier also and are used for cadmium, germanium dope detectors.
So, students, let us summarize what we have learned in this module. Vibrational spectroscopy consists of different types of spectroscopies, and reflection absorption IR spectroscopy, that is RAIR, is discussed. In this technique, a highly reflective surface sample is required to reflect the front face of the beam specularly. This technique employs the identification of molecular species present on the surface of the adsorbent. An oscillating dipole perpendicular to the surface of the metal is IR active. The dipole moment of the adsorbed molecule and the electric field of the incident light interact with the metal electron on the metallic surface, thus imposing metal surface selection rule, that is dipole selection rule, depending on the electric behavior of the metal. The metal surface selection rule states that the incident light should have a component that is P-polarized. The component having electric surface perpendicular to the surface, electric field perpendicular to the surface, is P-polarized due to destructive interference, and electric field parallel to the surface disappears. Here, P-polarized light is parallel to the plane of incidence and is almost doubled by reflection at grazing incidence. Therefore, only P-polarized component light can be reflected from surface at high incidence angles. The experiment is generally carried out with the sample placed in a UHV chamber, which is relatively large and used for a range of other surface analytical techniques. The infrared beam is extracted from the spectrometer, focused into the UHV chamber, reflected from the surface under consideration, and further refocused on the detector using the optical arrangement. Thank you.